Go. Okay, so we discussed the integral controller, and if you remember with the integral controller, let me kind of very quickly take a look at our last slides. Okay, so if you remember the integral controller, essentially the integral controller adds a pole to the system, and if it's used by itself, it actually increases the number of asymptotes in the root locus, closed loop root locus, by 1. So when the number of asymptotes is increased, usually that has an adverse effect on the stability, because as more asymptotes are added, the 360 degrees is divided into more kind of smaller angles, and some of these asymptotes necessarily go into the right half plane. So that means some of the branches will have to necessarily go to the unstable side, and that actually brings us to that actually causes quite a small area of a stable region, okay, when you want to place the closed loop poles. Okay. What is the upside of an integral controller? I guess the main purpose of an integral controller is to make the steady state error go to 0. So by adding by adding a pole at the origin, you increase the type of the system by 1, and whatever the original system is, basically you increase its type by 1. So for a self-stabilizing system, which is a type 0 system, right? If the plant is already type 0 and you add 1 pole at the origin, you increase the type by 1. So its unit step response ends up having a 0 steady state error. So that's one of the main motivations behind using an integral controller. But you can see that it has an adverse effect on the stability. So the next thing we will discuss is to combine the integral controller with a proportional controller. Okay, and we will see that that's gonna partially alleviate some of these issues. Okay, so let me go back to a clean slide. Okay, so let's call this case 4, and this is our proportional integral controller, where we combine the proportional gain with an integral gain. Okay, so let's say GC of S, our controller transfer function, this time is Kc, which is the proportional gain, plus Kc over tau I times 1 over S, which is the integral constant. Okay, so you see that this is still our dependent, so-called dependent ideal PID form. Okay, and this really kind of lays out why this form is so popular, because it's a PID form, a mathematical parametrization, which makes it quite intuitive to analyze it in terms of what are the effects of the different coefficients. So let me kind of make this or change this a little bit, manipulate it. So this becomes Kc times, we have basically S plus 1 over tau I, and I have an S in the denominator. Okay, so that is also Kc, let's call it S plus alpha, where alpha is equal to 1 over tau I, which is our so-called integral time constant, okay, divided by S in the denominator. Okay, so if you look at the proportional integral controller, what you see is that it adds an integrator, a pole at the origin, but it also adds a 0 at the same time at minus alpha, which is equal to minus 1 over tau I. Okay? So in order to analyze this, we do the same. We actually assume a certain value of alpha as a design parameter, and we investigate what's happening with the proportional gain Kc. So we again use root locus in order to see overall what's happening with different choices of alpha and as a function of Kc. Okay, so let's say again, assume a small tau I and consider root locus with respect to Kc. Okay. So what do we have? We have one pole at 0 and 1 0 at basically s is equal to minus 1 over tau I, which is equal to minus alpha. Okay, so overall we have one pole and 1 0. So that means we don't change the number of asymptotes in the sense that we don't add any new asymptotes or we don't reduce the number of asymptotes. Okay, so number of asymptotes unchanged. Okay. The important thing, or one of the important things, is that note, overall system now again type 1, because we still have this denominator integrator type 1, which means ESS will be going to 0 for a unit step reference and a type 0 plant. Okay, a type 0 plant often is also called a self-stabilizing plant, right? A plant which doesn't itself have an integrator. Sometimes you may have a plant which already have an integrator, in which case you don't need an integral controller because the denominator s is already there. Okay, so let's take a look at our original example. Our plant with two stable poles. So we have GC of S, G of S, our open loop transfer function, right? Sometimes we call it that way, is equal to Kc S plus alpha, the introduced 0, and in the denominator we have an S, S plus 1 and S plus 2. The two existing stable poles of the system. So how about, number of asymptotes again is equal to n minus m absolute value, which is 3 minus 1 is equal to 2 asymptotes. Angle of asymptotes, we know that it's going to be plus minus 90, but plus minus 180 divided by n minus m absolute value 2l plus 1, that's going to result in plus 90 and minus 90 degrees asymptote angles, the two unique asymptote angles. Okay, what about the centroid? Centroid rho 0 is equal to summation of the poles minus summation of the zeros divided by the number of poles n minus m. Okay, so that is equal to, in this case, our summation of the poles is 0, minus 1, minus 2, minus 3, summation of the zeros is equal to minus alpha. Okay, so minus alpha makes plus alpha, and divided by the number of asymptotes, n minus m is equal to 2. Sorry, n minus m, which is equal to 2 in this case. Okay, so that means we have minus 1.5 plus alpha over 2 is our centroid. Mind you that this centroid unfortunately now is a function of alpha. So by choosing an alpha, we can actually change where the centroid is. So we have a plus 90 and minus 90 degree asymptotes, but where we place them is actually a function of alpha. So we can put them in favorable locations, or we can put them in, problematic locations as well. So let me sketch the root locus maybe over here. Okay, so oops. Arkadaşlar bir kopukluk oldu. Şu anda beni duyabiliyor musunuz?
Evet hocam.
Tamam.
Şu an duyuyoruz hocam.
Okay. So our open loop poles are at the origin, at -1, at -2, and let's say that we place our 0 minus alpha over here. Okay. So what's going to happen is that we will have basically an asymptote intersection with the real axis, which is our this is going to be our rho 0 is equal to, remember, minus 1.5 plus alpha over 2. Remember, when we say a small tau I, a small integral time constant, we are basically saying relatively large alpha in absolute value. So minus alpha is quite small over here. We want it somewhere here. But that has an adverse effect, okay? Putting the 0 to the left-hand side is advantageous. But unfortunately, that's going to move our centroid towards the right. So that's not something desirable, because the asymptotes, if they cross to the unstable side, that would mean that they will eventually pull our root locus to that side as well. So in this case, let's see which part is part of the root locus. This region, where I have an odd number of poles and zeros. So root locus starts at the open loop poles. There will be a breakaway, okay? And then we don't know how, but that's gonna eventually approach these two asymptotes, okay, on this side. Over here, again, even number of poles and zeros, so this part is not part of the root locus. And then we come here between -2 and minus alpha, in which case, again, it's part of the root locus. Arkadaşlar beni duyabiliyor musunuz?
Evet hocam. Evet.
Tamam, ama çizdiklerim gelmedi. Bir saniye izin verin, bir ufak değişiklik yapayım. Şimdi geldi. Acaba tableti telefon üzerinden mi bağlasam? Neyse, şimdilik idare edelim bakalım. Çok kötü olursa değiştiririz. Note. Row 0 can be adjusted by the selection of alpha. Arkadaşlar bir şu tabletimi ben telefon üzerinden bağlayayım, daha iyi olacak. Çünkü iki bilgisayar bağlandığım için sıkıntı çıkıyor. Bir saniyenizi istiyorum. Du. Şöyle yapalım. Tamam. Tekrar paylaşıyorum ekranımı. Daha iyi olacağını umut ediyorum. Daha iyi oldu mu emin olamadım.
Hocam onu videolar geçerken ancak gözlemleyebiliriz. Böyle sabit ekranda falan.
Yo, sabit ekran değil ki. Şeye geçtim ben.
Ben de hala sabit gözüküyor arkadan.
Yo,
Şey
biliyorum
gözüküyor.
işte, sıkıntı orada. Yani ben biraz önce çizdiğim dokümana geçtim ama çok iyi bir şekilde gelmiyor o. Bir saniye. Ben aslında tablette şu anda şey paylaşmış durumdayım ama pek de Allah Allah, ilginç bir durum. Okay. Yok, böyle hiç olmadı. Allah Allah. Enteresan. Bir saniye arkadaşlar. Evet, şimdi daha iyi gözüküyor. Okay, so you see that we can change row 0 by selecting alpha, but it looks like the possible range is quite small, because if you increase alpha in absolute value, you very quickly move the centroid towards the j omega axis. Okay, so well, as another note, we can say for suitable choice of alpha, the system can be made stable, but with the advantage of zero steady state error. Okay. What about the settling time? Unfortunately, the settling time is not that great. Okay, you see that this centroid, in many cases, the centroid is actually quite close to the j omega axis. So that means as you increase the gain, okay, you will still be quite close to the j omega axis, and that means the settling time will not be that great. Okay, but if you think about why we were forced to increase the gain, it was because we wanted with the type 0 system to actually diminish the steady state error. That was the motivation to increase the gain. But in this case, since the gain is since the steady state is error is already 0, you don't need to too much change the gain. Okay, so you can still select a favorable gain in order to achieve a reasonable steady state error. So let me also put that note here. Okay, note. But we still cannot make the settling time very small. This was still a problem with the integral controller, but the integral controller also had stability problems. Now we fixed the stability problems, but unfortunately could not too much improve the settling time. Okay. Now the final thing I want to discuss, and then we will have our exercise, is case 5. Okay, so case 5 is the full PID controller. Okay, so case 5 is the proportional integral derivative controller, derivative or PID controller. This is the full version, and it's a very popular way controllers are applied in the industry, because you have 3 parameters now, okay, 3 different gains, and that gives you 3 degrees of freedom. Okay, we now have so-called 3 degrees of freedom, namely 3 different controller design parameters. Having 3 parameters means that you can have a very rich set of behaviors is achievable. But the disadvantage is that the design of the controller now is much more difficult, because remember, root locus gives us the ability to design for 1 parameter. If we have 2 parameters, well, we can sort of still survive, because we make choices for one of the parameters and still use root locus or other techniques to analyze the other free parameter. But once you have 3 different parameters, I mean, there is so many different combinations that it really becomes quite difficult. But still, we will make an attempt to make a choice for the 2 parameters and still attempt to use root locus for a similar purpose. Okay, so let me try to do that. So consider the following interpretation. Arkadaşlar çok yaşayın. Bu arada yazılarım biraz geç geliyor ama artık hani sözlü olarak da takip edeceksiniz. Interpretation with the dependent, again, dependent ideal PID parameterization. We also call this the form, right? PID form. So here is our controller transfer function. So it's going to be a controller proportional gain plus kc over tau I times 1 over s, which is the integral term, plus kc times tau d times s, which is the proportional term. So let me take this first into 1 over s parentheses. So that's going to be kc s plus kc over tau I plus kc tau d times s square. Let me also take it into kc tau d parentheses. So that's going to be kc tau d. In the denominator, I will have an s. So that's going to be s squared, a quadratic formula here, 1 over tau d times s plus 1 over tau d tau I. So you see that kind of everything becomes intertwined. All the three parameters have effect on each other. So you cannot really separate the design for different parameters. But essentially what you have is something like this, right? You have a gain, K, which is the combination of these two gains, Kc and tau d. And you have two zeros. Let's call them S plus alpha, S plus beta. And you have in the denominator an S. Okay, sorry, the writing is coming with a little bit of delay. Okay, but it's gonna be there in a minute. Okay, so I have the gain, I have S plus alpha, S plus beta in the numerator, and in the denominator I have an S. Arkadaşlar beni gene attı şeyden.